All right, I'm going to go ahead and start recording. I know I'm not connected yet, but don't worry, I will be. Let's go ahead and I'm going to boot up Studio One. All right, so auxiliary HDMI, plug in the power, plug in. Today's lesson going to be about compression. All right, so we've got ourselves and opening. All right, so for those of you who do not know, I have a hobby. And my hobby, and I have a couple different hobbies. If you, one of them, as you learned from last lecture, is I play a lot of video games, and I especially enjoy FromSoft's Elden Ring. I also enjoy the Paradox video grand strategy games, which are essentially giant board games so advanced you need a computer to do all the rules, so it's a video game. And then I also enjoy that, and this is what I got back into in the pandemic. I actually have a minor in music, and I enjoy not only writing music, but taking. I enjoy writing music. I enjoy remixing video game music, and I enjoy using basically machine learning, some different machine learning tools to generate completed versions. And I can show that some other time. But right now, what I want to talk about is just music technology and compression. And we're going to talk about compression in general, but I'm pulling this up because it gives me multiple concrete examples of just how important a topic compression is. So let me go ahead and delete the output files from this morning. So this is a program called a DAW, or a DAW. That is short for Digital Audio Workstation. You can think of it like this is basically an IDE for music production. Each row represents a musical instrument. For instance, this top one is the triangle, which give me 1 second to make sure that, there we go. So for instance, and so this is just simply an event saying, hey, hit that with a roll. Okay, I know, very, not super exciting here. So, but this is from a piece from that called Final Fantasy Legend 3, which was a Game Boy game for the original Game Boy, and then was remade for the Nintendo DS in Japan. The remake did not come out in the US. But the fun thing about Nintendo DS games is that you could essentially rip a lot of the music and information from them and the musical instructions. So I did that, and I've been working on this and orchestrating it. So this is what it sounds like. So this is the next one. Looping because I had the loop active. Not that it matters, we get the point here. So this is done using virtual instruments. Okay. The French horn, which is the primary horn I know how to, sorry, the primary instrument I know how to play. I'll solo that out so that you can identify it if you don't know what it sounds like. Now this is a very interesting instrument in the sense, virtual instrument, in the sense that this is made by a product called Infinite Brass. And what it does is that it is samples, which are recordings of the instrument, plus modeling. And specifically what the developer of this program did here is that he recorded the instruments, but then he also recorded the reverb separately and uses a bunch of clever programming to apply it. So I can just change the reverberation space, and rather it being echoey, it's a very dry sound now, as it's referred to, as opposed to having that echo trail. So that's one way of doing instruments, which is just basically sampling, which is basically just it's modeling them. And in memory, it is very tiny because Contact is a terrible program that hasn't updated the UI in forever. It uses 25 megabytes of RAM. Not too much, but there's some disadvantages to this. It's not really authentic in some ways. It is very realistic, in my opinion. But there are some issues with authenticity with that could come up because, for instance, the legato, this transition right over here, is simulated. It's actually done by some clever programming connecting those two notes. Basically, a legato is when you basically transition between two notes with no interruption. That's been simulated, which is really good simulation. I should add. But there are some purists who like to but this is a newer way of doing things. And the older and classical way is doing samples, which is you record everything in the room and you record, and if you want to do legatos, you record those transitions between the notes as well. And this is what we have with the string section over here. This is other virtual instrument. It sounds great, in my opinion. And these are samples that have been recorded by this is done by a company in the UK called Spitfire Audio. They have this product called the BBC Symphony Orchestra, where they sampled the BBC Symphony Orchestra and recorded them at their recording hall. So you get their, the really authentic sound. And, there's no simulation, no modeling going on over here. But if you, and I know it's tough to read, but this says it's 3.99 gigabytes of samples currently loaded so far. And that's shared between all these string sections, plus the flute and clarinet and glockenspiel I use, and some other instruments. But that's much, much, much more than the 25 that I was using here, because that was a lot of just programming handling it. And that's not the this on any way of doing it, but like it's with that, if it's 4 gigabytes in RAM, and that's just a small portion of the orchestra, I'm just using the strings and some of the woodwinds from that product, and it's the entire orchestra. So this version core is about 28 gigabytes of samples, compressed samples, I should say. The full version is 600 gigabytes of samples. Compressed. Uncompressed, it's more than a terabyte worth of musical samples. It's huge. Storing it on your computer requires you to have not just space lying around, but specific space dedicated. 600 is not chump change for most people. For a lot of laptops, you're walking around with a 256 gigabyte, hard drive if you're not really caring about, because most people don't need that much. So when you see like pro specs going up with 32 gigabytes of RAM, this is kind of music, audio, and image production is typically what they're talking about when you're talking about professional. right? Like for instance, my computer at home, my desktop at home has 48 gigabytes of RAM, and it's not for gaming. It's because I got way too involved in just doing music as a hobby. So think about that for perspective. If this company sent uncompressed audio, right? First off, that's a burden to the consumer. They have to have space to store that, right? That's and a terabyte hard drive is like $100 right now. Okay, terabyte SSD, a hard drive, much cheaper, like $40 for a hard drive. But nobody wants a hard drive because those things are slow as molasses. Think of the scene from Zootopia where they go to the DMV with the sloths. That's your hard drive as compared to a solid state drive. Okay, but not only that, right? You gotta host that. This is a downloadable product, right? You can buy a hard drive and have it shipped to you with the stuff preloaded, but then you're buying a hard drive. And that costs extra money. As opposed to like, but some vast majority of these products, which can range from 20 to 40 to 60 to 80 to all the way up to 600 gigabytes, needs to be downloaded. And if they weren't compressed, you'd be downloading a whole lot more. Okay. So that costs money for the company, not just in terms of storing it on like an Amazon cloud server, but also the download, the bandwidth costs. So having it compressed means that they also save on money that way. So compression, just like that kind of compression right there in a product is valuable. Like if you're serving something, you want to be able to send it out compressed. Now, but what we're going to be talking about for just a bit more is on the consumer side, because I've got this music, and I'm going to just go ahead and render it. I'm going to render it as an MP3 file and a WAV file just to kind of show you. Okay, so here we go. So I'm going to render this loop over here. So I'm going to render that into to a file. I'm going to save it as a file so I could like share it with anybody, right? Because that's the great thing about music production. You make music and then you share it. Okay. I don't, and part of this, I don't promote my stuff on class because I find that mildly, I find some ethical things with like, oh yeah, you should need to like and subscribe my channels. No, that feels exploitive. But you can probably do some searching and find the stuff I'm doing on YouTube. So let's go ahead. So I'm going to go ahead and save this to my desktop, select folder, and I'm going to save this as WAV output. Okay, so a WAV out is basically the oldest kind of file format for audio files that's still in use. It's I believe, it could be wrong here. I'm rendering 17 seconds of this. But basically what we're saving here is the sound wave, which is just a bunch of points that have been stored as it goes up and down and creates the vibrations in the air that hit our eardrums. And again, the mechanics of sound and how so many things just transform into a single signal, essentially, for us to digest. And here we go. There it is. This is the file playing. Now this is a 3.2 megabyte file, okay? But it's 17 seconds. The longer these files are, the bigger they get. Like, and this is just the music. And well, 3 megabytes isn't much nowadays. It used to be a heck of a lot. So what we would do is that we use compression, right? Because this is an uncompressed format, unencoded format. So one of the most famous formats for that is MP3. I'm sure you've heard of MP3. Like MP3 players, that meant music players essentially. And this is what we call a lossy compression. Because the idea here is that our human ears, they only have a certain range from about 20 to 200,000 hertz. Basically, that's the sound of the frequencies we can hear. But also, like, a lot of this musical information in the WAV file is coming at us fast. So if we just, threw away some of it, the human ear is actually not going to notice. So what I'm saying here is I'm going to select a 192 kilobits per second bit rate, which means that basically that I'm saying use every second. I want you to only dedicate 198 kilobits, because it's lower KB, not byte, kilobits, to recording, to basically encoding this information. And that puts a pretty stringent hard limit on it, and I'll record it and output it, and it renders just fine. Okay, and now let's see, we've got this, and now we've got a 400 kilobyte file, not a 3 megabyte, 400 kilobytes. So this is like 8 times smaller. And unless you have like really good ears or something, you're not going to notice any difference. And that difference might just be nocebo. It might just be a nocebo. And that works by throwing out information. But what do I mean? But what does it mean when we actually throw out a good amount of information? So I'll show you, like, what happens if we throw out a noticeable. So now I'm going to do throw out. I'm gonna lower that resolution to 64 kilobits per second. Okay, a small amount. Okay, so now it's a much smaller file, and you're gonna see that the output is going to be much smaller than our input, than our files have been so far. So now we've got a 135. It's about 4 times smaller, but this is what it sounds like. Sounds a bit crackly and like it's not got the same quality, right? It's more staticky almost, right? Right, as compared to, let's go ahead and compare it to the actual output. See here, we've got the drum hi-hat going, background. But now if we do like more kind of distorted, hard to describe because we're trying to describe an audio phenomenon. But it like feels like there's like bubbles constantly in the, just like trying to play through something that's bubbly, right? So there's some degradation though, but it's still the same song. And if you're trying to save space, that's great. Another more common form of compression is, let's go ahead and see Tom Scott. He did a video on Tom Scott video compression. This is a great video. I recommend watching sometime. Why snow and confetti ruin YouTube video quality.
Have you ever noticed that?
Let me just turn you down a bit. Right, and we've got this playing at 1080p, and he talks about basically how the video encoding format works and how certain things can really, how bitrate can affect stuff. It's really effective, and it shows just how things can how it works. It's really good. So but also notice here on YouTube that we have the ability to like manually lower the resolution, which means basically that we're downloading a different file essentially. So if I go down to 144p, I throw out more of the data. That's fine. And it looks terrible, but it's still the same video. And this is great for when you have like no internet, like when you have a really bad connection. It's not ideal, but it's a choice, because sometimes because of data limits or because you have bad connection, you need a smaller file. But overall, these are choices that can be made on the user end. But we do want, we all as humans like want the best quality and stuff. So compression is important because because we consume so much media. And if we can, if basically we can lower that bandwidth cost, then huge things happen. We can consume more of it. We can consume it in higher fidelity. We use less energy potentially. So it's cool. It's really good. But in general, these work with loss. These are a lossy format because there's things that we can throw away that your human eyes, unless it's at a really low bit rate, your human eyes just won't notice it. Okay. But that gets us to that's just one way of doing compression. The other way we can do compression is what's called lossless. And that's what this today's topic is going to be about, Huffman encoding and lossless compression. So let me just output one more, and we're not even going to listen to it, but we're going to output a FLAC file. FLAC standing for free lossless audio codec being compressor decompressor. And what it's going to do is that basically it's going to take that waveform and not throw away compress it without throwing away any information. Okay. And the trade-off here is that it takes time for the computer to uncompress it. Okay, that's the trade-off here. So, and we can see here that it's less than half the size. It's 1,300 kilobytes versus 3,200 kilobytes. It's a pretty good trade-off there. It's really cool that we can create that. And so why is lossless important though, if we aren't gonna, so why is lossless important? Well, it's important for people with the production have the production files. First off, from a creative perspective, you want those original files, just like you want the originals of film to when you make your production version. But also because not all data can be compressed lossily. So for instance, like text, for instance, we should not ever throw any information away. Your significant other texts you, hey, I'm feeling sick today, right? And then you text back, that's not good. And then you have a compression algorithm that throws away the not. That's going to be pretty terrible, right? Going to cause a lot of misunderstandings there. So text, it's very important. You can't throw away any of the data in text. And that's really what we're going to be looking at. We're going to be looking at, so that's what we'll look at. And that's our motivation. But we don't really talk about compression too much in classes. And I never had anybody kind of demonstrate, but it's one of those things that is important enough that there's an HBO TV show entirely dedicated to it, Silicon Valley. It's all about a magical compression algorithm that's better than everybody else's and what they do with it. So, and shenanigans and stuff. But okay, so let's go ahead and, so Huffman coding. So Huffman coding is the way is one of those ways that we compress that we can encode text. And we should talk about the way that text is currently encoded before we can get into that. Again, Tom Scott has a very amazing video. Tom Scott, UTF 8, which if you want to learn more about the way this, watch this video by Computer File, Characters, Symbols, and the Unicode Miracle, right? But Unicode is based off of this, is a development of one of the first milestones in our communication, which is Ascii, the American Standard Code for Information Exchange, which basically it basically said, hey, these are the binary sequences these are the standard binary sequences that we're going to use for letters and strokes on your keyboard. Right? So works began on it in 1961, and then it was proposed in 1963, most recent update in 86. Realizing how long ago those were and feeling old. So, but anyway, the control chart looks like this. Basically, each character you send a byte, each character is 7 bits. So we have 128 unused characters that we can use for anything else. But basically, if you wanted, and this is what characters are. That's why you can add characters together like they're integers. You've got null, start of text, /t for your tab, /n for your new line, right? And so if a computer gets a byte that has 00001010, it knows that's a new line. Okay. And your character, and then everything else on the American keyboard is here. Space. So space, exclamation point, all the punctuation, all our numbers, everything that's on a keyboard in here, including, and this most importantly, those letters. Okay. There is a kind of a disadvantage. There's kind of a glaring hole though here in Ascii and using it as an international standard. And that is, what's the glaring hole in using Ascii, the American standard, as an international standard? And that, of course, yes. There's a lot of other languages, and not all of them use the Latin alphabet. Never mind, basically, the Germans and their umlauts, you know, or you know, those, at least those have Latin characters, right? But if you're learning Japanese, you note that basically you've got you've got two syllabaries and a third writing system called kanji. And those, well, let's see. Let's see. Yes, there are 200. Yeah, there is Kyoiku kanji, which is the 1026 first kanji characters that Japanese children learn in elementary school. That's a bit more than 128 or 256. That's actually quite a bit more. That's a lot. That's a lot of characters. That's a lot of characters that have to be rendered individually, and being able to copy that entire character and then hit paste, right? And then I have to be able to send that character to a computer, another computer on the web, who can read that character and decode it. Right? There's a lot, and give me some information about it. There's a lot that goes on for communication. And so that has been extended by Unicode. Unicode extended this, which is basically has more than enough space for all the symbols and all the strokes and all the glyphs, and we can do arbitrary ligature marks, which is part of the reason you get stuff like Zalgo text, because it abuses parts of just how amazingly strong Unicode is. Unicode is awesome. And this just simply used a bunch of this abused just a ton of the ligature marks that can be, and characters and additions and stuff that can be added to characters, and subscripting and superscripting that can be done in Unicode to kind of break it. And I can copy this and paste it, and you can see it's like all messed up over here, and I can totally, and it just like breaks out of everything. So anyway, the Unicode is awesome because you can do a lot with it. But so this is great for like encoding characters, but it's not great for compression. We don't want to use this scheme for compression, because we could do it a different way for compression. Right now, every single character has the exact same amount of bit length in Ascii. That's what we're going to focus on, just Ascii, right? The letter E is encoded, or the letter lowercase e is encoded 1100100. And it's got the same number of bits encoding it as X does. But E occurs a heck of a lot more than X. So the idea here for how we can save space is we change the encoding scheme. We say, let's use less bits on the more common characters like E, and more bits on the least common characters like Z. We'll make E relatively short and Z relatively long. Make sense? Okay. So, but we can't just simply come up with a generic kind of compression for everything. Well, like a generic encoding, I should say, for everything that every document is going to use. right? Every language has a letter frequency, has a, so in English, right, here's the frequency, relative frequencies. E occurs the most often, Z occurs least often. It's different. This fingerprint for each language is different in each language, but we can't just use this for every arbitrary text. For instance, like if I were to use E as the most, always assume E is the most common letter, that would be wrong because that my compression algorithm would fail in examples of constrained writing, like Gadsby. Gadsby is a novel written in 38, 39, Gadsby. There we go. 1939. I got it right, 1939, Gadsby. It is a novel written that does not include the letter E in it whatsoever. So making E the least costly character there would be wasteful because we don't use E at all. So we don't even need an encoding for it, right? Similarly, if we're not using any funky umlauts or the like, we don't need to include those either, right? And again, this is partially, I mean, this is 1939, so no internet to distract this guy for, so, you know, part of the reason why he probably wrote a novel like this. There's other awesome examples of constrained writing because, you know, like Thing Explainer by Miranda Monroe, which she basically tries to write a book explaining things using only the 1,000 most common words, trying to describe how a internal combustion engine works when you can neither use the words internal combustion or engine. And those produce kind of very interesting things because constraint creates creativity. That's part of the reason why we emphasize learning how to use stacks and queues, even though you could use a linked list for both of those. Because once you're locked into thinking like a stack or a queue, that changes the way you're going to think about how to solve a problem. But so what that means in practice is what we're going to do is that we are going to create a frequency count for each document that we're trying to compress. And what we'll do is that we will send the encrypted, sorry, not the encrypted, but the encoded information, the thing we encoded, and then we're going to give the person who got it a key on how to unencode it. So I'll go ahead and use this Wikipedia example where we have the Huffman generated tree for, this is an example of a Huffman tree. That is a bit long, I think. That's a lot of characters. Probably don't want to use it. But what they do is they generate this and say, hey, space is the most frequent, so we're going to use only 3 characters for this. Same with A and E, only 3 characters, and everything else gets progressively longer. So I'll do what I did earlier, which is generate random DNA sequence. There we go. We're just going to go ahead and generate a random DNA sequence of, let's go with 35 characters. All right. So what we'll do is I've copied that, I put that into Notepad, and now I'll go ahead and I'll show you how we work with this, okay? So the first thing we need to do is count how many of each characters occurs. So C, cannot find C. Very good. Oh, because I said not find C. How interesting. Great, Notepad, you fail again. So match case, find. And let's go ahead. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 C's. So that's the first thing we do to do Huffman encoding. We do a frequency count. Now the T's. 1, 2, 3, 4, 5 T's. C occurs 11 times. T occurs 5 times. Okay, and now the A's. 1, 2, 3, 4, 5, 6, 7, 8. I believe that's 8. We'll know if it adds up to, if it adds up to the right number, we'll get it then to 35. It'll be fine. And then G's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. G 11. Let's go ahead and 1, 2, 3, 4, 5, 6, 7. So is this 35? It looks like 35, yeah. Let's go ahead and add, just even though it's probably going to be wrong, another G to the end, just so that we don't have to deal with any ties. Okay. I'm going to do 12 G's. Okay. Make sense to everybody? So first thing we do to create, we need to do is figure out what our encoding is doing this. And we do this by building a Huffman tree. The first step in building a Huffman tree is building a priority queue. And remember, a priority queue is just a queue that we can cut in line for. So we'll go ahead and order these things. So T goes to the front of the queue. Let me go ahead and put it up here. T goes to the front of the queue with its value of 5. A8, C11, and G12. Okay. And now we build our tree from here. And what we do is we dequeue the first, basically we have a while loop that runs while the queue, this is the queue, has more than one thing in it. We do 2 steps. 3 steps. We dequeue the first two. We dequeue the first 2 things in the queue, combine them, and then add it back into the queue. Those are our 3 steps. So dequeue the first 2 things. T and A get dequeued from our queue. Okay, and that was 5 and 8. And what we do is that we combine them. And what that does is that the first thing goes on the left, the second thing goes on the right, T and A, 5 and 8, and we create a new node as the root node, as their parent node. It is a combined weight that has a weight of 13. Okay, why 13? Because that was 5 plus 8. And now we go ahead and add 13 back into here as PA. Okay. Now what we do is that we are going to add C and G together, because those are the next 2 things. Now, had this been smaller than one of those? Yeah. Sorry, give me a second. I'm going to change this problem under your feet again. So this is what it would be if it was 13. Sorry, if there were 12 G's. But let's go ahead and add some more arbitrary number of G's so that I can just emphasize how a priority queue works. GG, GG. So that was 1, 2, 3, 4. So we're up to 16 G's now. Okay. Probably some terrible mutation at this point. Okay. So that becomes 16. So now, right, we've dequeued, we've combined them, we've added T and A together, we've got 13, and the node is TA. Okay. So now we have to reorder the queue, because with the priority queue, things cut in line. So our queue becomes C, TA, G. C, TA, and G. G is 16, C is 11, 13. It's ordered by the weight. So now we dequeue the first 2 things in the queue again. C and TA. C. Okay. The way this works is that to combine them, we create a new node with the first thing that came off on the left and the second thing that came off on the right. And we put their weights together. So this becomes 24. And then we put it back into Q. For G, and then CTA, Chicago Transit Authority, is now 24. And now we add them together. Sorry, and now we DQ again. G goes on the left. The new node at the top goes on the right. And it has a combined weight of both of them, 40. And now we only have one, and now we only have one thing in the queue. So let me go ahead and make that a bit easier for us to read. We have G, T, C, A, okay. And that was our final answer, with this having a combined weight of 40, but those weights are no longer important now that we're done with that. So that is how we will encode our sequence. Okay. So now the question is, how do we encode this? Okay. And the answer is that what we do is that we put ones and zeros on our branches. Zeros go on the left branches, ones go on the right branches. And it works as follows. So and what we do is that basically from the root we figure out what the path is to get our sequence. So so G, being the most common, is a 0. T is 1 0, C is 0 1, and A, sorry, C is not 0 1. C is 1 1 0, and A is 1 1 1. Okay, makes sense? You go from the root to G is a 0, from the root to T is a 1, then a 0. To get to C, it is 1 1 0, and to get to A, it is 1 1 1. So now the way we encode that is as follows. So C is C is 1 1 1. Sorry, C is 1 1 0. T is 1 0. A is 1 1 1. I'm just going to do the first six characters. C is 1 1 0. A is 1 1 1. A is 1 1 1. Okay, so that's just the first 6 characters. Okay, so if I give you this tree and this sequence, how do you translate it? Well, you start at the root and you follow. You go, okay, I've got a 1 1 0. So 1 1 0. 1 1 0. That brings me to C. Okay. 1 1 0 brings me to C. 1 1 1 0 brings me to T. And 1 1 1 brings me to A. 1 1 0 brings me to C. 1 1 1 brings me to A. 1 1 1 brings me to A. So CTA, CAA is how we got them. So this is essentially how it works. And it ends up being much. So long as basically the compression means that that the instructions on how to, the compression plus the instructions on how to uncompress it are smaller than the original text, it's good. And so Huffman coding is extremely efficient in this regard. Now, I wanted to go over this because I've done so in previous semesters, and up until COVID hit. And then I started taking it out of the curriculum just because there was too much to go over, I felt, with all the things going on. So I bring it back because I think it's a valuable experience to know about compression and compressing video and audio, since we work with that as programmers so much. but I'm not going to put it on the exam or the final exam like I typically do. I just think it's very valuable for you to know about. I think it's very valuable. And so you're going to look out because I'm probably going to bring it back once things get back to normal in fall. Ostensibly, things should be back to normal then, because ostensibly everybody's going to be vaccinated at that point, who can, or every age group is eligible to be vaccinated, I should say. So, but compression is big, and it's kind of an invisible force that helps shape basically a lot of the stuff we can do on our devices every day. So with that, I just want to I'll be up for taking demos and for taking test corrections. Please have your test corrections turned in by Friday. And the reason I have this Friday deadline, which I'm going to mention, it's not a hard deadline. If you need more time, send me an email. But the idea here is the reason it's a deadline is because I don't want to have to, deal with this into the end of the semester. I don't want to have to be dealing with I don't want to have to be have students try to get things corrected at the end of the semester. So just try to have it turned in by Friday, and if you need to show me after Friday, that's perfectly fine. Okay, I understand, and just send me an email if you're running late on it. Okay, if you're open with me, I'll be open with you. So there you go. So let's go ahead and stop recording.